Okay, I'm working 13.7, number 19. We have this surface integral. Here's our surface S. We have a cylinder, radius 1, that comes out the x-axis. We're looking in the first octet and we're cutting it off between x is 0 and x is 3. So let's see. X equals 0 is the YZ plane, and our cylinder comes out this way, so it's going to do something like this, and then it's going to wrap around the back side, but we're only in the first octant. It's going to come down like this to x equals 3. Okay, we'll have something like this. Okay, see if that makes sense to you here. Cylinder, radius 1, that's 1. And this is x is 3. X equals 0 is the back side. But all we're interested in is this surface right here. Okay, this part of it is the S. And we're trying to find this surface integral. So when we look at this surface, right, we want to see how can we draw that surface. All right, so let me work on trying to come up with some parameterization of the surface. All right, it doesn't look like it's going to be an easy one to write where z is a function of x and y, or y is a function of x and z, because I can't solve this easily for one of those variables. So let me try and come up with this parameterization. We'll take care of all the other details afterward. So I want to draw the cylinder. It's this outside edge, using the YZ plane to draw circles. So I'm looking at something like, since the radius is 1, I'm looking at something like cosine u, sine u. That should draw me unit circles because the radius here is 1. I only want my u, I only want to draw these quarter circles. Okay, so I want my u to be bounded between 0 and pi over 2 instead of 2 pi, which would draw me all the way around. And then my x-coordinate, I want to start at 0 and come out to 3, so I'm going to let this be v, and let v be between 0 and 3. And that should draw me what I need. Okay, now the next thing is to go ahead and find the cross product of this. So let me move my restrictions over here. U is between 0 and pi over 2. V is between 0 and 3. Now, when I do my partial with respect to u, partial of r with respect to u, I get 0, okay, and then I get negative sine u. Then I get cosine u. When I do the partial of r with respect to v, I get 1, 0, 0. Now remember, what I'm trying to do here is get this part of it, ds. And ds was the magnitude of the cross product of the partials, right? dA. Okay, so that's what I'm going for here. The cross product here, partial r with respect to u, cross the partial of r with respect to v, is going to be a vector. We'll cover this up here. We get zeros there. And cover this up. We get 0, and then we get negative cosine, or minus cosine u, but it's the middle one, so it's positive cosine u. And we cover this one up. We get 0, and then minus and negative, so it's going to be plus, so we get sine u. And then when I take the magnitude of that, it's the square root of this squared plus this squared plus this squared. These two squared and added together is a 1, so we just get 1. So we just get 1, which is really, really nice. So now we're ready to go ahead and do the surface integral. I'll do it over here. And I can go ahead and convert this over now to my restrictions here on u and v, which constitutes my d region here. So we get double integral. Let's go 0 to 3 0 to pi over 2. And then I'm going to have this, which I need to plug in my component function, or the components of my surface. So the z is sine u, so I've got sine u plus x squared, which is going to be v squared, and then y, which is cosine u, and then times this, which is this, that's a 1. So times 1, I'm not going to put it, and then dA is du dv or dv du. In this case, I'm going to go du dv. All right. So this is it. Now we just integrate that with respect to v first, and then with respect to u. Let me just tell you what the answer should be here. You should get a 12 here. Okay, that's it for that one. Let's take a look now at number 21. So now we're switching over to surface integrals over vector fields. So flux. Number 21 is the first example of this. And we have evaluate f dot ds across the vector field. They give you the field is, let's see, converting this over, we've got z e to the xy. We've got negative 3z e to the xy. And just do something, make sure I didn't do this one. Yeah, I did not do this one, okay. And then xy, like that. So there's our field, and then the region S is the parallelogram of exercise 5. So exercise 5, I did that earlier. It was this. R of uv is, let's see, u plus v, and then u minus v, and then z was 1 plus 2u plus v. Our restrictions here were that u is between 0 and 2, and v was between 0 and 1. Okay, so that's what we had from number 5. Now, I'm going to save myself some time. I'm not going to go through and do everything I have to do here because we already did it earlier. So I'm going to be using the formula that this is equal to double integral, and let me see, in the notes, I'm referring to, that's good, formula, let's see, 1377, so we're going to go F dotted with R u cross R, partial R with respect to V dA. So I need to find the cross product of these partials, which we did in number 5. And let me just look that up real quick so I don't have to redo it. The cross product, when we did the cross product, let's see, I'll put it right here. When we take partial of R with respect to u and cross it with partial of R with respect to v, we should get the vector, we got the vector 3, 1, negative 2. You can check back in the video for number 5 that we did in fact get that. Now, here they say that they want the upward orientation for the parallelogram. So, you know, we have this parallelogram three-dimensionally. Okay, whatever it looks like in three-dimensional space. That's our S. And we want our normal vectors, okay, to be pointed upward, okay? So we don't want them going kind of into the parallelogram and down. We want them to be coming out like this. So we want our cross products to make sure that they're coming up. And so you can tell when you look at this right here, if this is our cross product, notice that the Z component is negative, which means these are actually the ones that are pointed downward, okay? That's what that actually is, all right? This is what we have because of the negative component here, but we want them to be up. So what we're gonna need to do in our formula is we're gonna need to change the signs of this. We're gonna have to take the negative of this, which will still be a normal vector, it just will point in the opposite direction. This is the one that we're gonna use, okay? That's ours. So you have to pay attention to that subtle little detail there. And then at this point, we can start putting things together, but let's see, I'm gonna use the F, which is this, dotted with this right here, but I also need to evaluate F on my surface. So I need to now set up, I think I'll do it right underneath this. What is, just separate work, because I'm trying to get these two parts. I've got this part, okay? Now I need F. That's really the field evaluated on the surface, like that, which is a vector. It is the vector, let's see, Z, which is this, 1 plus 2u plus v, e to the x times y. X times y, notice that's a difference of squares. When you multiply those, you get u squared minus v squared, comma, now this, negative 3z, so negative 3 times the z, all right, and then e to the same thing, e to the u squared minus v squared, and then the last part is x times y, which again is u squared minus v squared. All right, I've got to take that now and I've got to dot that with this. So now I think I'm ready to set up this double integral right here. So I have double integral over the region D. D are my restrictions on u and v. F evaluated at the surface, which is this. Okay, getting there, and then u squared minus v squared. I want to dot that with this vector, which is negative 3, negative 1, 2, and then dA. And hopefully, if we're lucky, the way they made the problem, things are going to get nice here. Let's see. So when I dot negative 3 times this, and then watch. When I do negative 3 times this, I get negative 3, 1 plus 2u plus v, e to the u squared minus v squared, plus, because it's a dot product, negative 1 times this makes that a positive 3, and then 1 plus 2u plus v, e to the u squared minus v squared, and then plus 2 times this, which is 2u squared minus v squared, all right, dA. So all of that. And notice that these two are opposite in sign, but they're exactly the same, so those go away. Gosh, we got real lucky there. So this equals the double integral, and then I'll go ahead and put the limits of integration on here now. Our restrictions are let's see, 0 to 1 on V, and 0 to 2 on U. And then I've got the 2, I'll bring the 2 out here, and then I've got U squared minus V squared du dV. And that's it. That's a pretty straightforward integration here. And when you work through that, you should get 4. Okay. Let's take a look now at number 25. So we have vector field given here, has the components x, negative z, and y. That just looks really familiar. Okay, it's not. And then S is the part of the sphere in the first octant. S is the part of the sphere x squared plus y squared plus z squared equals 4 in the first octant. All right. And they want us to use orientation toward the origin. All right, well, first thing we need to realize is what we're working with here as far as the surface. So we're in the first octant, and we're looking at a part of the sphere, the surface of the sphere with radius 2. So the back side's like this. This curves over like this. And so we have this part of the sphere. Right, so we've cut out part of the sphere like that, kind of. So it's only the part in the first octant. And we're actually looking at this surface. So it's this curved surface on the outside here towards us here. Okay, and that's our S. Also, we want to keep in mind that the normals that we have, we don't want them pointing out, okay, that we want them to point in. All right. So we're going to need a couple of things here. We need to find some parametric representation of the surface, and to kind of cut back on time, I'll just ask you to remember, well, which one am I doing? Number 25? Oh, okay, yeah, we can do this several ways. I like the way the book does it because it uses one of our formulas. Now, generally speaking, we could not look at this surface as a function of two variables because it's not a function because it's the whole surface or the whole sphere. But if we're just looking in the first octant, just looking at the parts where z is positive, then we could take this if we wanted to and solve it for z and take the square root and only have to worry about the positive square root because we're not looking at negative z values. So this right here can be our surface, and we can look at our surface as being a function of just two variables. Now we have this sheet with these surface integrals in the special cases. I'm looking at the top case. Now it says that our flux ds should equal the double integral over d of negative p times the partial of g with respect to x minus q times partial of g with respect to y plus r dA if our normals are pointing upward. but our normals are not pointing upward, our normals are pointing inward. So what happens is we change this to a positive, we change this to a positive, we change this to a negative. And then remembering that the P, Q, and the R here are just our components of our field, and then G is this, then all we have to do is compute that, this multiplication, these partials, and we're there. We do need to figure out what our restriction on D is, but we'll get that in a second. All right, so let's now set this up. Okay, this is going to equal to the double integral over D of, okay, P here is X times the partial of G with respect to X. So the derivative of this with respect to X is 1 over 2 square roots of 4 minus X squared minus Y squared times the derivative of this with respect to X on the inside, which is negative 2X. That's just chain rule. Plus Q is negative Z, times partial of G with respect to Y, which would be very similar to what we just got over here. It'll be times 1 over 2 square roots of 4 minus X squared minus Y squared, but this time times negative 2Y. Okay, and then we have minus R, which is Y, dA. Now that doesn't look very pretty. I agree with that. I'm wondering if I should clean this up. Yeah, let's clean this up just a little bit. This will be, I don't need this. Double integral over D, X and X here, and then these twos cancel. We get negative X squared over square root 4 minus X squared minus Y squared. And then here, these cancel. We get negative Y, right? But then times Z. Remember, what is Z? Well, this is Z, right? That's Z. So also notice the negative and the negative become plus. So really I'm going to have Y times this, but this is the same as this, so these are going to cancel, right? When I plug this in right here, these cancel. So all I have here is just plus Y. And then the last part is going to be minus Y, dA. And these Y's cancel. And we get double integral over D, negative X squared over square root 4 minus X squared minus Y squared dA. That doesn't seem right, but let me see, which one am I doing? 25. No? Okay, that's good. All right, so now at this point, I need to think about how I'm going to figure out what D is. Now remember that we're working with this surface here, which was this part of the sphere up here. My question is, how can we figure out a restriction on X and Y? Right, this is our XY plane that would draw that surface. Remember, this is G of XY. And if you notice this down here, that's a great polar region, right? In two-dimensional XY, 2, that's a really, really nice polar region. So what I'm going to do is I'm going to convert this double integral over to polar, and I'm going to put some restrictions here. I'm going to put theta between, let's see, 0 and pi over 2. And I'm going to put my R restricted between 0 and 2. And remembering all my things that switch, right? X becomes, in this case, R cosine theta, and X squared plus Y squared, and all that stuff is R squared. So this double integral is going to go, let's see, 0 to 2, 0 to pi over 2. And I can go either way, right? Doesn't matter. Negative x squared is going to be negative r squared cosine squared theta over, and then here, remember this, I can look at that as being negative x squared plus y squared. X squared plus y squared is r squared. So we get square root of 4 minus r squared. And then don't forget that we also get an r and then dr d theta. What I'll do is I'll switch these. So pi over 2 here and 2. And so we can start cleaning this up a little bit. I like the idea here of, let's put this here with this r, and well, let me write it down and maybe you'll see what to do from there. So 0 to pi over 2, 0 to 2, and now r cubed, negative r cubed over square root of 4 minus r squared, and then dr up cosine times cosine squared theta dr d theta. That's just rearranging things. And notice the r's and the thetas are separated by multiplication, so I can turn this into two integrals and multiply them together. So this is integral from 0 to 2 of the r stuff, negative r cubed over square root 4 minus r squared dr, times integral from 0 to pi over 2 of cosine squared theta d theta. Okay, now I'm just debating on whether or not I want to actually go through and do this. Yeah, I think I will. I am going to pull this negative out. Maybe I'll leave it. Let's leave it. Okay, so on this integral right here, let me do this. I'm going to work this completely through. And that first integral, it's going to be, let me just look at this. How about being a little clever here? Rewriting it like this. And then I'm going to make a substitution here. U is equal to 4 minus r squared. The derivative of that is negative 2r dr, which means negative, I have a negative r up here. So let me just divide both sides by 2. So 1/2 du is negative r dr. So what I notice is negative r dr is going to become 1/2 du. 4 minus r squared is u. And then to figure out what r squared is going to become, just solve this for r squared. So move the r squared to the other side, subtract the u. R squared equals 4 minus u. So just that integral right there becomes, see, the 1/2 came out, 1/2 du. And then on the top, I have the r squared, which is 4 minus u. And on the bottom, we have the square root of u. And you can split that into two different problems. So 1/2 integral 4 over this root is the same as 4u to the 1/2. And then minus u over root u is u to the 1/2. Negative 1/2 here, sorry. And then du. All right, now we just do some antiderivatives. Add 1 to that, you get a 1/2. Flip it 2, you get 8. So 1/2, this is 8 u to the 1/2. That's the antiderivative of this. Check it. 1/2 comes out, that's 4. Subtract 1, you get that. Antiderivative of this, so minus 2/3 u to the 3/2, just adding 1. And then we replace our u with what it was. So I'll do that on the next, I'll do that when I go back up here. Now, for this one, I'm going to look at that one. Just remember what u was here when we switch back. U was equal to 4 minus r squared. Okay. So for this integral, cosine squared, I'm going to rewrite that as 1/2 plus 1/2 cosine 2 theta. It's just a pre-cal identity there. And take the 1/2 out and get 1 plus cosine 2 theta d theta, and then antiderivative of this, 1/2 theta, antiderivative of that is plus 1/2 sine 2 theta. All right, so we should be in business here. I think we're ready. So we will now evaluate both of these integrals. This one is this, and why don't I just pass the 1/2 through here? 1/2 and 1/2. That'll be a what, a 4, and over here that'll be a 1/3. So I'm going to have 4 square roots of u, okay, minus 1/3 4 minus r squared to the 3/2 evaluated 0 to 2 times, now this one is 1/2 times theta plus 1/2 sine 2 theta evaluated 0 to pi over 2. All right, so let's plug in 2 first. So we plug in 2 here. We get 2 squared is 4. We get 0 here. We get 0 here. So everything's 0. But then we get 0, and then we go minus. Now let's plug in 0. If we plug in 0, we get 4. Square root of 4 is 2. 2 times 4 is 8. So I'm going to get 8 minus, let's see here. 0 here is 4. 4 square root, that's what that means. Square root of 4 is 2, but then cube it, that's 8. So I'm going to get minus 8/3. Then times, over here, when I plug in pi over 2, I get, let's see, 1/2 pi over 2 plus sine of, let's see, 2 times pi over 2 is pi. So sine of pi is 0. So that's gone, nothing. And then I go minus, and now when I plug in 0 here, get 0 and sine of 0, 0. So we just get zeros here. So it's looking like, at the end of the day here, we're having, let's see, 8/3. Let's get a common denominator here. Multiply top and bottom by 3, so you get 24/3 minus 8/3. Which is going to be 16/3, but it's going to be negative, so negative 16/3. And then over here, this looks like times pi over 4. And that doesn't look right. Let me see. Yeah, but it is. Okay, this 4, so I get negative 4 over 3 pi. Negative 4/3 pi. All right. That was interesting. All right, let's look at one last one here. Number 29. So for 29, I'm going to be doing a slightly different approach. In which case, I'm going to, okay, let me write down the problem first. Let me erase all this. All right, we have 29, our field, which is x, 2y, 3z. All right. And then the cube, we have S is the cube with vertices plus or minus 1, plus or minus 1, plus or minus 1. So we have actually all these different combinations of these points. So let's take a look here. Okay, this is our x, so if we do 1 and -1, okay, so let's imagine we have 1, 1, 1. We can have -1, 1, 1. We can have, let's see, 1, -1, 1. We can have 1, +1, -1. Let's see if we've got all the different combinations here. Negative, negative. We can have -1, -1, +1, and -1, -1, -1. Oh my goodness. Let's see, 1, 2, 3, 4, 5, 6. Let's see if I've got all these. Negative, negative. No, I could do 1, -1, -1. And I feel like I'm missing one. I know I am. Should have a total of 8, because it's a cube, right? So maybe it'd be easier just to do it this way, right? You got 1, 2, 3, 4, 5, 6, backside 7, 8. So somewhere in the backside of this, got that 8th point. Yeah, let's just do it this way. I kind of like it if we just draw it like this. Now, we know that the x, y, and z axes come out through here. Let's see. Punches through the center there, and then it comes out over here, punches through the center there, something like that. It's about as good as I think I'm going to get. So really the most important thing is to understand what each of these faces look like in terms of surfaces. So we're going to have, what, 6 surfaces, a total of 6 surfaces. So let's look at this front surface right here, S1. Let's just do that. What is that? S1, all right, has the equation that your x-coordinate is out 1, and then every other point lies in that plane that's parallel to the yz axis. So x is 1, and then we have restrictions, okay, which we could set up restrictions, all right? I'm not going to do that. Well, I'll do it just for this first one. Y is between -1 and 1. Z is between -1 and 1. All right, we could continue to do this. S2, let's let that be the top one. S2 is z equals 1, and then I can do restrictions. S3, let's let it be this one right here, this front face. That would be y equals 1. And then for S4, let's do this back side here, which would be x is -1. S5, let's let that be the bottom right here, S5, which would be z equals -1. And then finally S6, what are we missing? Y is -1. So those are the 6 surfaces, and we're trying to evaluate the flux. So let me do it here. Trying to figure out what the surface integral over S of f dot ds is, but there's an equivalent double integral of f dot n ds, where S is the surface area, right? And remember what the definition of this was, okay? The definition of this was RU cross RV and dA. That's what that was. But this is the magnitude of RU cross RV dA, right? So there's a difference between those two. And this one, what's nice about this one is this right here, this vector is just the normal vector of the surface. And with all of these surfaces, we have very nice normal vectors. And they tell us in the problem, well, we assume because it's closed that our normals are going to go outward. So like for S1, notice that since this is just a flat sheet, the normal vector would come straight out down the x-axis, out the x-axis. So for S1, the normal here, I'll say normal 1, will be equal to the vector, it's going out the positive direction of the x-axis, 1, 0, 0. I know that for sure. So that means that if I'm trying to find the flux on S1, I just need to take F and dot it with the normal of the first surface 1, ds, which would be double integral over the restriction, or over S of, well, what is the F, what is this dotted with 1, 0, 0? So I'm taking X, 2Y, 3Z, and I'm dotting it with 1, 0, 0, which just gives me X, S1. So I've got double integral over S1 of X ds. But on S1, what is X? X is 1. So this is just double integral over S1 of 1 ds. And that's just the surface area, right, of S1. And the surface area of S1, we know this is a square, right? Right, now be a little careful here because this goes between -1 and 1, -1 and 1. So the length of this is 2 and the length of that is 2, so the area of that is 4. So the surface area here is 4. Now that makes things a lot easier, right, than doing anything else. Let's try, okay, that's just one of them. Let's try and do S2. So for S2, I think what I'll do is I'll erase this one. Okay, so for S2, by the way, we're going to add up all these answers. So the flux over S2, F dot the normal over S2 ds. Okay, what's the normal vector of S2? Let's see here. S2 is z equals 1. This one points straight up like this. So the normal of S2 is 0, 0, 1, right? Straight up. It's basically k hat. And so this becomes the double integral over S2 of x, 2y, 3z, dotted with 0, 0, 1 ds. And that just gives you 3z. So we get double integral over S2 of 3z ds. But on S2, z is 1, so that's just going to become a 3 here. And then what we can do is we can just factor out the 3, and we get 3 double integral over S2 of ds, 1 ds, which is just the surface area. And again, we know the surface area of that is, they're the same for all of them. So this is going to be 12, 3 times 4, so 12 here. All right, let's do S3. Maybe I'll move a little quicker. S3 is coming out towards us this way. It's kind of hard to see it, but it's coming out this way. And so for S3, the normal vector of S3 is going to be 0, 1, 0. And let's see if we can move a little faster now. This is going to become S3. This is S3, or N3. This changes to 0, 1, 0. And when we dot that, we get 2y here. But y here on this one is 1, so we get a 1, but we pull the 2 out. And the surface area of S3 is 4, so we're going to get 8 here instead. So 8. So far we have 4 plus 12 plus 8. And let's go now and do something a little more interesting. How about S4? So S4 is this backside, And the normal vector sticking out of that points this direction, which is the vector -1, 0, 0. So let's see how that changes things. I hope you can tell what that is. This is coming out the back side, so that hits that face and goes out, away. Okay, so, okay, so we're going over S4 here now. The normal of S4 is -1, 0, 0. And then when we plug in, when we dot this, we get -x here. -x. Hold on just a second. Yes, ma'am.
Are you busy right now?
What do you got?
Well, I was going to take your class fall this year.
All right, sorry about that, got distracted. Where was I? Yeah, so we get -x here when we dot these together, but pay attention here. Notice that on S4, x is -1, right? X is -1, so when you change this, it'll become -1, that'll give you +1. We won't have a 2 out here anymore, so you'll get the surface area of S4, which again is 4. And I'll finish it up. For S5, the normal vector is pointing down, so that's the vector 0, 0, -1. And I believe if you work through all that again, you're going to get 12 again. And then if you work through the other one, you're going to get 8 again. So you should have this plus 4 plus 12 plus 8, which is, what is that? 24 and 24, 48 should be the flux for that one. So there you go. Notice I didn't use any shortcuts. any formulas, I use that other formula, which is very convenient if you know these normal vectors are always staying the same, right? So when you have flat surfaces, that works really, really good. All right, that's it for 13.7.